Okay, so in this last lesson of the unit, we're going to be looking at limiting reactant, percent yield, and ending on some combustion analysis. In this first problem, we're to determine the moles of CO2 and H2O formed. So we're looking for moles of both of these products. Moles of products. When 2 moles of ethane and 10 moles of oxygen are reacted in the reaction. So what makes us need a limiting reactant in this problem is the fact that we have information about 2 of the reactants. Both of the reactants have an amount, and the other one of them isn't listed as in excess like we have had in past problems. So in order to figure out what the limiting reactant is, meaning which one runs out first, we have to do something called finding moles of reaction for each of the ethanes and the O2s. So when I start this problem, first order of any of these problems is to start with moles. Luckily in this problem you're given moles, so we don't need to convert. If you're given grams from the beginning, you have to convert to moles. So I'm going to start here and I'm going to say, okay, I have 2 moles of ethane. And then I also know that I have 10 moles of oxygen. So when I see that, first step in limiting reactant is to divide by the coefficient in the balanced equation, because for every 2 of these we need 7 of those. And when we do so, we get here a 1.0, and what is that number? That number is moles of reaction. What does that mean? That's how many moles of the reaction that can be produced when we utilize 2 moles of ethane. Well, let's go ahead and look at good old oxygen. When we divide that by 7, we get 1.4. So 1.4 moles of reaction is how many moles of reaction that can be produced when we start with 10 moles. So which substance limits the amount of product that can be produced? It's this guy. We produce less moles of reaction by starting with that many moles of C2H6. This one we say is in excess. So now when we do our stoichiometry, we're going to go from here directly to our products and do 2-dimensional analyses. So I'm going to do 2 separate. I'm going to start with my moles of C2H6. So I've got 2.00 moles of the C2H6. And then I know that for every 2 moles of that, because of the balanced equation, I have 4 moles of CO2. So that means how many moles of CO2 do I have? 4. And that's how much product I have there. And next I'm going to look at H2O. If I start out with 2 moles again, I start with a limiting reactant. For every 6 moles of water, I have 2 moles of H2O. So that gives me 6 moles of H2O. And that's how I do limiting reactants. So let's go ahead now and take a look at another limiting reactant problem. This time we're starting from grams. So in this problem, I'm having 50 grams of each of these guys. And the goal is to figure out how much of this product will be produced in grams. So again, I have to look at my 2 reactants and figure out which one is going to run out first. So I'm going to start with my 50 grams of calcium. First step is always to convert to moles. So I'm going to divide. For every 1 mole, I get 40.08 grams of calcium. So my number of moles of calcium is 1.25. Okay, so nitrogen, again, 50 grams. For every 1 mole, I have 28.02 grams. That's from the molar mass from the periodic table. It's a diatomic, and that gives me 1.78 moles. So once I have moles of both my reactants, I could figure out moles of reaction by dividing by the coefficient in the balanced equation, 3 and 1. And whichever produces less moles of reaction is going to produce less product, which is going to be considered the limiting reactant. So when I divide here, I get a number that's 0.4 0.416 moles of reaction. And then when I do look at this guy, this is just going to be 1.78 moles of reaction. So we know that this is less moles of reaction, therefore this is the limiting reactant, and then our nitrogen is what is in excess. So when we do our stoichiometry, we're going to go from here to that bad boy. And be careful, you want to just use your moles, or you can start with 50 grams if you want, but you already went to moles, so I'd start with moles of calcium and then go to your product. Never ever use this moles of reaction for anything other than figuring out what the limiting reactant is. You might be asked specific questions about moles of reaction later in the year, but right now that's its only purpose. So now we're going to go ahead and do dimensional analysis. We're going to start stoichiometry with our moles of the calcium. So that's 1.25 moles of calcium. For every 3 moles of that, we're on the mole bridge already because we're already in moles, I have 1 mole of the calcium nitrite. And then for every 1 mole of that calcium nitrite, it is 148.26 grams per mole. All right, all that cancels, leaving me with grams, and I end up with 61.7 grams of calcium nitride. 3 sig figs is based on the number of sig figs found in front of the limiting reagent, which is calcium. All right, next problem, methanol. This is a combustion example, and if you look, this is about percent yield. Percent yield, if you remember the formula from Chem 1, is actual yield over theoretical yield times 100. Actual yield is what you find in the lab or what you've done in the lab. In this problem, they give you the actual yield because they say that's what's actually produced. To find percent yield, our job then will be to do math to find theoretical. Anytime you're supposed to find theoretical, you're solving with math. So the first thing I need to do is write an equation. This says carbon monoxide and hydrogen, when mixed, is going to yield your methanol. So whenever you have to write a reaction from scratch, please check your balancing. And you can see that I need a 2 here because I have 4 hydrogens on the right side. So first order of business is to write down what I have. I've got 68.5 kilograms of this, and I have got 8.60 kilograms of this, and I'm looking for my theoretical yield, which I'm going to plug in there to find my percent yield. So in order to know which one I'm going to do dimensional analysis from, I have to find the limiting reactant. So I'm going to convert those grams to moles. I'm just going to immediately make this 68,500 grams and 8,600 grams, and I'm going to divide each by the molar mass. The molar mass of CO is 28.01, and the molar mass of H2 is 2.02. And when I do that, I get moles of 2446. Then when I figure out how many moles of hydrogen I have, that comes out to be 4258 moles of hydrogen. Now, in order to figure out the limiting reactant, I'm going to divide both by the coefficient in the balanced equation to get moles of reaction. This gives me 2446 moles of the reaction. If I used my hydrogen, it would give me, math is hard, 2129 moles. Well, that's going to be less moles of reaction than the CO, so this is my limiting reagent. This is an excess, so I'm going to do stoichiometry from there to there to figure out what my molar mass, what my theoretical yield will be. So let's start with the moles. Really important when you do your problem, go back to the moles, not the moles of reaction, because the moles of reaction is not utilized in that way here. We're going to take these moles and start a dimensional analysis. So I'm going to get 4258 moles of H2. For every 2 moles of H2, I have 1 mole of good old methanol. And for every 1 mole of methanol, I have 32.05 grams. That gives my theoretical yield of value of 6.82 times 10 to the 4th grams. So that's my theoretical yield. So now to find actual yield, I'm finding percent yield, I take the actual that was given to us in the problem, actual over theoretical times 100. My actual yield was 3.57 times 10 to the 4th grams. My other one is 6.82 times 10 to the 4th grams. That's theoretical. Again, I used math to determine that. When I do all this beautiful stuff, I get a 52.3% yield, which is what the problem was asking for. What's nice about the AP exam and the use of some of the problems that they give you there is that they will not ask you multiple problems in the stem of the question. If they want you to do multiple things, there's a different part for each, and they lead you through the process. So ultimately, they want to know the percent yield. But rather than just asking that, they're going to take you through it step by step, as in this problem. So our first order of business is to find the limiting reactant. As indicated, the information given to us is that we have 2.5 grams of this guy, 4.5 grams of this guy, and 4.0 grams of this guy. And our goal is to find the percent yield of that substance later on down the way. So first thing we want to do is find the limiting reactant. So I'm going to go ahead and find moles of each of these. 2.50 grams of the AS2O3 divided by the molar mass of 197.84 gives me 0.0126 moles. And then let's look at iodine, 4.5 grams, divided by the molar mass of 253.8 gives me 0.01774 moles. And then last but not least is my water. My H2O is 4.0 grams divided by 18.02 is going to give me 0.222 moles of each of those. So now my next step to figure out the limiting reactant is to divide each of these by the coefficient in the balance of equation to find moles of reaction. And this is divided by 1, 2, and 2. That gives me 0.0126 moles of reaction here. This gives me 0.0087 here. And this gives me 0.111. Go mental math. And again, these are moles of reaction. The limiting reagent is then going to be the one that produces the least moles of reaction. So it looks like I2, producing that many moles of reaction, is our limiting reagent. These guys are going to be in excess, and we're going to utilize that to find the percent yield eventually. On the AP, how you would answer this question then, I'd need some sort of statement from you, and the answer to this question would be I2 is the limiting reagent or reactant because it produces the least moles of reaction. That's it. That's as simple as it gets. And we expect that kind of explanation when you're asked why that happened. That's what we want to hear. Whoa, I'm going crazy. I don't know how I flipped that. That was weird. Okay, so there's the statement about moles of reaction. We're going to keep that in line here. Calculate the mass. That's theoretically possible. So now we're going to take those moles that we just said were the limiting reactant moles, 0.1774 moles of our I2. And we're going to go, okay, so for every 2 moles of I2, I have 1 mole of AS2O5, and then for every 1 mole of the AS2O5, I have 229.84 grams. That's going to give me a final gram value of 2.04 grams. That is my theoretical yield because I did math to get there. Part C says if only 1.8 was actually produced, what's the percent yield? Oh, remember percent is actual over theoretical, so my actual is what I actually produced over the theoretical that I just solved times 100, I get 88.3% yield. Dun, dun, dun. That's a little better than the last percent yield problem, that's for sure. Okay, our final problem is one of those combustion analysis problems. We had a homework a while back that had this on there, and a lot of you were like, how do I solve this? Well, now you get to learn, and you'll be able to go back and solve that problem. So here we're combusting a hydrocarbon. A hydrocarbon is something that contains carbon and hydrogen. We do not know what the formula is, but we do know it's combusted, and when we combust it, we make CO2 and H2O. The only thing they give us in this problem is the amount of this that we start with, and then it tells us that in the process we produce 0.0103 grams of carbon dioxide. So in order for us to find the to find this empirical formula, which is the goal and ultimately the molecular formula, I need to know grams of each of those things, either grams of each of those or moles of each of those. The problems that you did for homework, remember you were given percents of each element, and then you're like, oh, I got to pretend those are grams. Well, that's what we need to figure out. We're going to need to figure out, we know the total grams, but how many grams are carbon and how many are hydrogen? This depends on what we call our conservation of matter. Notice that we have CO2 here. CO2 is the only place carbon is in our products, right? So all the carbon in here then had to come from here. So whatever I find out as the amount of carbon in this molecule, that's going to be the amount of carbon that came from here. Once I know grams of carbon that's in here, I can subtract from this total and get grams of hydrogen, and then I'm just going to treat this like a normal empirical formula problem. So let's go ahead and start with our information about our CO2. If I have 0.0103 grams of CO2, I'm going to, as always, convert to moles first. So for every 1 mole of that, I have 44.01 grams. And then I know for every 1 mole of CO2, this is the kicker, I only have 1 mole of carbon. We got to get to carbon. For every one of these, I have 1 of those. So carbon then I can convert to grams because I know the molar mass of carbon to be 12.01. So doing this gives me a total gram value of 0.00281 grams of just the carbon. Well, knowing that, I can take my original amount of naphthalene, 0.0300, subtract off this carbon business, and that will give me just grams of hydrogen, which comes out to be 0.00019 grams of just hydrogen. That's it. That was the hard part. Now we're going to treat this just like a normal empirical formula problem, and you're going to make a little table here, and we're going to solve for our empirical formula. So we know we have 0.00281 grams of this. We know we have 0.00019 grams of this. When I divide by the molar masses to get moles, I get 0.000234. Exponential scientific notation works really well here too, 0.00018881. Now, now this is moles of each, right? So now what do I have to do? I always divide now by the smaller of the two. Don't get this confused with limiting reactant. We're taking both moles and dividing by the smaller. Not anything to do with the coefficients in any balanced equation or anything crazy. So when I do that, I get a 1 here, and I get a 1.25-ish here. Well, I can't have a formula that says 1.25H1, right? So I need to multiply by a factor, and it's going to be 4, and it's going to give me C5H4. This is my empirical formula. Now, how do I know I did that right? Well, the best way to tell is to look at the molecular mass they give you. They give you it was 128. The empirical formula mass, when you figure that out, comes out to be 64. So when you divide your empirical formula mass into your molecular mass, you get a whole number. That's how you know you did it right. That is a multiple of 2. So our molecular formula turns out to be C10H8. And sure enough, that's what naphthalene looks like. It's 2 benzene rings. Boom, boom. Oh, I didn't do that right. It's here and here and here and here. And that's mothballs. That's what we use for mothballs. That's it for the day. Only thing else to look out for is you're going to have some problems where you are given, for instance, let's say you have an O in here. If you're asked to find all 3 elements, you will be given information. You'll be given the grams of water. So you'll get your grams of hydrogen from your water. You'll get your grams of carbon from your carbon dioxide. And then you'll subtract both of those from the total to get your grams of oxygen. So be prepared for problems like that because you will see those. All right, that's great. That's it. Have a great day.